因为这有什么特别的？有吗？是你摆的阵。
被挡到，挡到。
Okay, the second and third talk this morning will be given by Masahito Yamazaki on geometry of 3D n equal to 2 theories. Okay, so thank you for the introduction. First of all, is this on? Yeah. Can everybody hear me? Great. Well, first of all, let me thank the organizers for invitation. And this is my second visit to Taiwan, so that was, if I remember correctly, 3 years ago. But even compared with 3 years ago, I could see that this string theory community here is growing, which is to my pleasure. And so today I'm going to talk about the geometry of three-dimensional N-2 theory, and which as it looks like might look like a little bit of string combination, but in fact this is geometry of three-dimensional N=2 theory. So it's not just a single theory, but a class of theories or many theories. And so that's the difference. But to simply put, that's the difference from many of the ideas works about the 3D gauge theories. In that, well, I'm not just going to consider a particular theory, but just a class of theory, and then try to discuss if there are any interesting structures there. So firstly, let's see. So roughly speaking, the structure of my talk is well, first I'm going to give us somewhat lengthy introduction and try to spell out some somewhat philosophical motivations. But partly because I don't expect anybody to stay until my third lecture, especially my third lecture is in the morning tomorrow. So, so I hope I myself can make it. But,
that will happen tonight.
So let me try to outline why I'm doing this. So I want to give a somewhat lengthy introduction at the beginning, and then I'm going to discuss 3D=2 theories and their dualities and afterwards I'm going to discuss the connection with three manifolds or 3D Chern-Simons theory. So roughly what I hope is that I'm going to be done with these lecture 1 and 2 today, and then talk about this tomorrow. That's my plan. Which means that if you do not want to miss the three manifold part, which is the most interesting part of the story, you should come. So let's see. So let's start with some somewhat philosophical questions. So so today I'm going to talk about supersymmetric gauge theories, and let's see. So and then I always remind myself of the story when I first came to grad school to study this field theories, and then
But the feeling thing about the high energy series, high energy students today is that there are so much things to learn. And well, of course you have to learn some dynamics, electromagnetism, etc. But then you have to learn the quantum field theory, West-Bacher, supersymmetry, and then maybe Weinberg textbooks, even Vicious, or Polchinski, etc. And then you might get tired. And then from that viewpoint, it looks like there is a fancy thing called a string theory, and that's the end result. And you should aim for that. And then in order to aim for that goal, you should pass through some unnecessary complications, including the field theory or and things like that. And so you have to suffer with all these complicated things. And so, well, of course, it's true that their field theory has various applications to condensed matter or cosmology or things like that. And that's one justification, huge justification for applying field theory is a huge area, which is rather important. But I was at that time questioning whether there is anything really interesting fundamentally as to the formulation of quantum theory is concerned, remaining, which I could do. So that was the question I have. But now I think I can confidently say that at least there are actually a lot of things we can do about the physics of supersymmetric gauge theories, even at the fundamental level. And so that's one of my main messages. So I want to begin with somewhat very very vague question. So what's the quantum field theory? And well, this is a very big question, and I'm sure that very different. Well, many people have different answers, and well, maybe it's matrix, as in the talk yesterday, or I mean, etc., etc. But let me try to be conservative, and there is a tentative answer. And so the tentative answer is to open the quantum field theory text. We can see what it says. And then, well, for example, well, not all the quantum field theory textbook is like this, but then, well, one thing is that let's start with the Lagrangian. So this is a sacred object, and then write down all these complications, tree diagrams, doing groups computations, fine diagrams, etc. And then you extract the physical observables. And physical observables is something you can measure. For example, there is a cross section, which is absolute sphere of amplitude, or I don't know, there is a Wilson loops, expectation values, etc. So there are a lot of interesting physical observables. So in a sense, all this quantum field theory textbook does is to try to tell you what's happening inside this huge black box known as the quantum field theory. So that's this one way to look at this quantum field theory. In fact, I think it's the conventional way of looking at quantum field theory. Now, well, of course, there are some fundamental questions to ask. Well, suppose that this is physical prediction, so we can compare with the experiment. And so this is our nature in a sense. Well, of course, nature doesn't mean that we really observe it, like since I'm going to consider supersymmetric series. But at least this is the physics in a sense. But of course, the question is, what happened to this Lagrangian part? So, well, in reality, we want to explain some nature, and it should come up with some Lagrangian. So what we should do is to try to go backwards, and then try to see what the Lagrangian is. And so this type of problem is known as the inverse problem. And of course, it's a complex problem. And it's important in various contexts. Like for example, in LHC, I mean, people discover something, and then what's the theory describing that. And some condense, well, some collider people are seriously working on this inverse problem, for example. Now, but that's not the reason I'm talking about that. And the reason is that there are some interesting subtleties because of the fact that this Lagrangian description and these physical predictions are not quite the same. And not quite the same in the following sense. So, well, for example, there are various different situations. So, for example, it might happen that there is a Lagrangian. So, well, the Lagrangian, it has a Lagrangian, and there are many parameters. And, well, let's see. So, first of all, what's the principle to determine this Lagrangian? And, well, and there is one sort of very, very beautiful answer, which essentially goes back to Ken Wilson, that the quantum field theory is just an effective field theory. So there could be some crazy theory like a strings of quantum gravity, etc. In the finities, QFT is an effective theory. And as far as that is concerned, let's see. So in order to determine this Lagrangian, you specify some inputs, like for example the symmetry. And symmetry could be gauge, for example, or it could be global symmetry, for example. Or, for example, it has matter contents. What kind of matter? The R. And then probably interaction. Well, the matter content, specify the matter content. So what I mean is that, say, if there's a standard model, let's take the gauge group S3 times S2 times U1, and the matter content does, for example, left-handed bulk is transform 3, 1 with hypercharge 1/3, or things like that. But anyway, so this is the matter content. And once you specify the symmetry, the matter content, you write down all the possible terms which is consistent with the Lorentz symmetry. So, and then write down all the terms. And quite often you impose renormalizability. Renormalizable renormalizable terms in the Lagrangian. And this is the most elegant way, in a sense, to formulate standard model, for example. And then it contains many parameters. And of course, there are some questions about which you determine by comparing with the nature. And at that parameter, well, there are some questions of how to think about these parameters, like cosmological constants, etc. But that's a separate issue, which I'm not going to discuss. So in principle, there are some parameters, and we could do that.
Why are you demanding renormalizability?
Sorry?
Why are you demanding renormalizability?
Well, I mean, it will depend on the situation. So, I mean, I want to, right, so, I want to, I mean, well, okay, so, what I'm going to be interested in is actually the infrared behavior, high infrared behavior of quantum field theory.
But many, well, depends on the question you're asking, but many things are dominated by the leading.
Yeah, that's right. So that's precisely the viewpoint of the text field theory. So, for example, if you have a high Lagrangian SN broken to SN, there are many derivative terms, for example. So in that case, I think okay, so if I remember correctly, the high derivative terms contribute to momentum, for example. So if the momentum is smaller than the scale of the theory, like pi mass, etc., and then you can neglect that contribution, for example. So you can try to. This doesn't mean that you drop by hand. So these terms are there, but you can. It's but you can.
But in some process, the leading contribution comes from those terms.
Yeah, I mean,
and you cannot neglect them.
Yeah, sure.
The theory, then you neglect the relevant, right?
Yeah. I mean,
no, so I mean,
so that depends on the situation. So right, so yeah.
Because an effective field theory is not important.
Yeah. That's right. I agree. That's right. Yeah, that's right. So I mean, also that's related to the question of what do you mean by effective field theory, for example, in a sense. So, right. So, but anyway, so.
Can I complain about something else?
Sure. That's what I was expecting.
So the Lagrangian is also a very redundant thing, right? So
That's exactly what I'm coming to.
Okay.
Yeah, that's right. Yeah, that's right. In fact, that's the complaint, right? So this is a beautiful story, and the quantum field theory textbook tells you that this is the answer. But of course, there is ugly. The Lagrangian is ugly in a sense.
You think we'll complain there's no need for Lagrangian?
Yeah. In fact, that's the precise. So I'm resonating with what you said yesterday. So in fact, Lagrangian is ugly.
There are different definitions and things.
Yeah, sure. So this is the story. But of course, the question is, well, so what's this symmetry, for example? What's the matter content, etc. So Lagrangian can be determined by these principles, but what are these things? And in particular, so there is, for example, gauge symmetry. This, which is, well, as in Newton's law, this is, in a sense, ugly. Well, the presence of gauge symmetry is a requirement if you impose the Lorentz symmetry, if there is a massless spin one particle, and if there is right, so, and you want to manifest the Lorentz invariance in neutrality, and you require to have the gauge symmetry. And that's explained in, well, for example, if you want a textbook explanation of that, please look at the volume 1 of Stephen Weinberg's textbook, which I confirmed in section 5 yesterday. And so, right, so there is an explanation subsection for the need for gauge symmetry, for example. So for example, that part there explicitly explains why gauge symmetry is needed for that. So gauge symmetry is needed for that purpose, for Lorentz symmetry in unitarity. So we cannot do away with that in a sense if you want to have manifest Lorentz description. But of course the subtlety is that, as is often also written in textbooks, gauge symmetry is a redundancy. So we can get rid of it, in fact. So that raises the question that maybe there could be several different descriptions of the same physics with different gauge groups, for example. And it's very conceivable that such things could happen, precisely because it's a redundancy. And then now, so interesting things could happen, especially if you have a gauge group, gauge theory. So there are interesting things that happen. For example, we have Lagrangian parameters, and they describe our Mother Nature. Or there could be some different Lagrangians with different set of parameters describing the same theory, describe the same physics. Or sometimes you don't even have a Lagrangian, or there is no Lagrangian, but maybe there is a S-matrix still. And then that still makes sense as a theory. So there are also all sorts of things that happen. So this is this Lagrangian, although beautiful in a sense, but at the same time ugly, in the sense that there are huge redundancies, potentially. So maybe I should write down here. And well, redundancy, but the Lagrangian could be different completely, or there could be redundancy in the set of parameters. So this is the subtlety, which is present in the conventional formulation of quantum field theory. So the question is whether we could understand this better. In fact, that's the question I'm coming throughout this lecture. Now there are interesting examples of such dualities. And especially, there are some proposed duality for non-supersymmetric cases. Well, the most established cases of these interacting dualities. Well, okay, so first of all, in these cases, these theories are called dual groups. Or if there are three, triarity, or n-arity, or web of dualities, so these are, it means that they describe the same physics. Now, there is an interesting example of S-duality, which I think is the most prototypical one. Example of duality. Oh, maybe I should write that. Examples. Well, for example, one good example is for the n=4 supersymmetric Yamazaki theory. And you don't have to know the precise matter content of whatever. It's just a gauge theory with some the super partners. And let's take this gauge group, for example, UN. And then this theory has one parameter, complexified parameter, and the natural combination theta plus 2 pi and I 4 pi squared over t squared. Oh, sorry, 4 pi over t squared. Where this is a Z angle. So this is the gauge coupling. And then the well-known statement, which passes many non-trivial texts, is that the theory for the n=4 super-MUs with gauge group UN, or with the complexified gauge coupling tau, is the same as the same theory with tau goes to -1 over tau, or more generally, tau goes to a tau plus b. C tau plus d, where ABCD is in SL to Z or PSL to Z. And in particular, if the theta angle is 0, this means that, in particular, this one is typical called S transformation. So G squared goes to 1 over G squared. So small coupling goes to large coupling. And so this is a strongly weak coupling duality. And that's a surprising conjecture, and people have verified that using the, for example, spectrum of solitons. And more recently, there are checks of that using the total loops and computation total loops and and they match with the Wilson loops for the dual gauge group, for example. So this is a beautiful duality. And the point that the reason I mentioned that is that in this case, the Lagrange in a sense is the same, but there's a redundancy in the parameter. Now, there are more drastic examples. And that includes, for example, the 4D n=1 cycle duality, which is the most famous duality probably in 4D n=1. And if you go, well, this is explained in many textbooks. And well, for example, there is a good textbook by John Ernie, which discussed 4D n=1 and their dynamics. Now, and well, let's see. So 4D n=1 cycle duality. So what's the statement? So the statement for this is that you start with the SUN NC gauge theory with NF flavors Q and Q tilde. Now, and then this theory is dual to SUNF minus NC. And NF flavors Q tilde, and then they also call the meson view M with a superpotential term MQ tilde, Q tilde MQ. Well, the details of that doesn't really matter. I mentioned this superpotential, etc., just for completeness. And if you have never heard about it, don't mind. The point is that this is a duality where the gauge groups change under duality. So this is SUNC, and this is SUNF minus NC. So the lengths of the gauge groups are different. So in this discussion, you might have SU3, but this could be SU5. So these are different. Which shows very convincingly that indeed there is no fixed notion of gauge symmetry once, even if you're given a particular physics. So this is an example where we have a different Lagrangian, and different parameters, but it describes the same physics. Where in this case, describe the same physics means that, right, so this is asymptotical free theory. So there is a gauge coupling constant, and the gauge coupling constant runs along this renormalization group flow. Well, by the way, I'm going to assume some familiarity with some very minimal QFT, including what the renormalization group flow is, or etc. And also, I'm just going to assume minimal knowledge of 4D n=1 supersymmetry, including some, say, first several chapters of Westbacher, but not anything else, basically. So right. So it means that I could use talk about RG flow, and then the point is that this theory has gauge coupling constant G, and this also has G prime. Now and then this theory is flow. The conjecture is that this theory is flow. So this is theory 1, theory 2, and if you go to the IR, so this is the UV. Well, sorry, I have in mind the conformal window case, so there is a constraint on NF minus NC. But anyway, right, so NF plus, well, just for completeness, 3 NC. So, no. What's this? Okay. Yeah, and no. Was this okay? Okay, and then they flow to the same fixed point at IR, where G and G prime becomes large. So this is an interesting example for another reason. The first reason, as I said, is that the gauge groups are different. But the second reason is that what I mean by the same, dual. In this example, there are different theories. So if you compute something in the UV, they are different. But in the IR, if you go to lower energies, these two theories are the same. They float to a certain fixed spot. So this is an example of such duality. Now, so I'm going to talk about three-dimensional series. So there is one good example for 3D duality. And these are called the 3D media symmetry. So, and then there are various different types. But let me mention a particular one. And I will come back to this example later in my lecture. And the particular version I have in mind is the following. So I have, so that one is called SQED with one flavor. So what I mean by this SQED, it just means that the gauge group is U1. And then one flavor means that there are fields, which in this case are n equal 2 chiral multiple. Well, I'm going to explain the chiral multiple, vector multiple, etc. A little bit about the 3D and n equal 2 basics afterwards. But anyway, so this is the matter, this is the this is the vector multiple. And no super. So this is one theory. And the dual theory in this case is the so-called XYZ model. And this XYZ model is a model where we have three n equal 2 chirals. X, Y, Z. And you have a superpotential, X, Y, Z. So as I said, I'm going to come back to this example later, and this plays crucial roles in the correspondence with 3 manifolds. But for the purpose here, the important thing is that here, the gauge group is U1. But here, I didn't write explicitly. That gauge group is trivial. So this is an example of duality between gauge series and non-gauge series, which is another example showing that the notion of gauge symmetry is not necessarily fundamental for describing the physics. So there are many dualities. So one question is whether we could understand all these dualities.
Sorry, so this equivalence is only true in the infrared?
Yeah, well, let's see. Actually, in this case, not exactly. So in fact, I'm going to talk about this correspondence with the mass terms included. So it has a scale. But the correspondence itself works with the mass scales included. Yeah, that's right. So I'm going to explain hopefully more about this later. But please keep this in mind. Right. Now, so these are the dualities. So in this case, everything is the duality. Right. So in this case, it's not 2 series the same, 2 series the same. Oh, okay. So maybe aesthetic reasons I should okay. Right. Now, you could do more, in fact. And the idea is the following. So suppose that there are, so these are the duality. But I could discuss wave of duality.